vector search fast and efficient. Like many other mechanisms that generative AI applications depend on, vector search isn't unique to generative AI. Vector search is common in any application that uses embeddings, search, recommendation, data organization, information retrieval, clustering, fraud detection, and more. Vector search is typically framed as a nearest neighbor search problem. For example, given a query, find the k nearest vectors. The naive solution is k-nearest neighbors, KNN, which works as follows. 1. Compute the similarity scores between the query embedding and all vectors in the database, using metrics such as cosine similarity. 2. Rank all vectors by their similarity scores. 3. Return k vectors with the highest similarity scores. This naive solution ensures that the results are precise, but it's computationally heavy and slow. It should be used only for small datasets. For large datasets, vector search is typically done using an approximate nearest neighbor (ANN) algorithm. Due to the importance of vector search, many algorithms and libraries have been developed for it. Some popular vector search libraries are FAISS, Facebook AI Similarity Search, Johnson et al. 2017, Google's SCANN, Scalable Nearest Neighbors, Sun et al. 2020, Spotify's Annoy, Bernhardson, 2013, and Henslib, Hierarchical Navigable Small World, Malkoff and Yashinin, 2016. Most application developers won't implement vector search themselves, so I'll give only a quick overview of different approaches. This overview might be helpful as you evaluate solutions. In general, vector databases organize vectors into buckets, trees, or graphs. Vector search algorithms differ based on the heuristics they use to increase the likelihood that similar vectors are close to each other. Vectors can also be quantized, reduced precision, or made sparse. The idea is that quantized and sparse vectors are less computationally intensive to work with. For those wanting to learn more about vector search, Zillies has an excellent series on it. Here are some significant vector search algorithms. 262, Chapter 6, RAG and Agents. LSH, Locality-Sensitive Hashing, Indik and Motwani, 1999. This is a powerful and versatile algorithm that works with more than just vectors. This involves hashing similar vectors into the same buckets to speed up similarity search, trading some accuracy for efficiency. It's implemented in FACE and Annoy. HNSW, Hierarchical Navigable Small World, Malkoff and Yashinin, 2016, HNSW constructs a multi-layer graph where nodes represent vectors, and edges connect similar vectors, allowing nearest neighbor searches by traversing graph edges. Its implementation by the authors is open source, and it's also implemented in FACE and Milvus. Product quantization, Jago et al., 2011. This works by reducing each vector into a much simpler, lower-dimensional representation by decomposing each vector into multiple subvectors. The distances are then computed using the lower-dimensional representations, which are much faster to work with. Product quantization is a key component of FACE and is supported by almost all popular vector search libraries. IVF, Inverted File Index, Civic and Zisserman, 2003. IVF uses k-means clustering to organize similar vectors into the same cluster. Depending on the number of vectors in the database, it's typical to set the number BR of clusters so that, on average, there are 100 to 10,000 vectors in each cluster. During querying, IVF finds the cluster centroids closest to the query embedding, and the vectors in these clusters become candidate neighbors. Together with product quantization, IVF forms the backbone of FAISS. Annoy, Approximate Nearest Neighbors. Oh yeah, Bernhardson, 2013. Annoy is a tree-based approach. It builds multiple binary trees, where each tree splits the vectors into clusters using random criteria, such as randomly drawing a line and splitting the vectors into two branches using this line. During a search, it traverses these trees to gather candidate neighbors. Spotify has open-sourced its implementation. There are other algorithms, such as Microsoft's SPTAG, Space Partition Tree and Graph, and FLAN, Fast Library for Approximate Nearest Neighbors. Even though vector databases emerged as their own category with the rise of RAG, any database that can store vectors can be called a vector database. Many traditional databases have extended or will extend to support vector storage and vector search. Comparing retrieval algorithms. Due to the long history of retrieval, its many mature solutions make both term-based and embedding-based retrieval relatively easy to start. Each approach has its pros and cons. Term-based retrieval is generally much faster than embedding-based retrieval during both indexing and query. Term extraction is faster than embedding generation, and mapping from a term to the documents that contain it can be less computationally expensive than a nearest neighbor search. Term-based retrieval also works well out of the box. Solutions like Elasticsearch and BM25 have successfully powered many search and retrieval applications. However, its simplicity also means that it has fewer components you can tweak to improve its performance. Embedding-based retrieval, on the other hand, can be significantly improved over time to outperform term-based retrieval. You can fine-tune the embedding model and the retriever, either separately, together, or in conjunction with the generative model. However, converting data into embeddings can obscure keywords, such as specific error codes, e.g., Edenotevail, 99, or product names, making them harder to search later on. This limitation can be addressed by combining embedding-based retrieval with term-based retrieval, as discussed later in this chapter. The quality of a retriever can be evaluated based on the quality of the data it retrieves. Two metrics often used by RAG evaluation frameworks are context precision and context recall, or precision and recall for short. Context precision is also called context relevance. Context precision out of all the documents retrieved, what percentage is relevant to the query. Context recall out of all the documents that are relevant to the query, what percentage is retrieved. To compute these metrics, you curate an evaluation set with a list of test queries and a set of documents. For each test query, you annotate each test document to be relevant or not relevant. The annotation can be done either by humans or AI judges. You then compute the precision and recall score of the retriever on this evaluation set. In production, some RAG frameworks only support context precision, not context recall. To compute context recall for a given query, you need to annotate the relevance of all documents in your database to that query. Context precision is simpler to compute. You only need to compare the retrieved documents to the query, which can be done by an AI judge. 264, Chapter 6, RAG and Agents. If you care about the ranking of the retrieved documents, for example, more relevant documents should be ranked first, you can use metrics such as NDCG, normalized discounted cumulative gain, MAP, mean average precision, and MRR, mean reciprocal rank. For semantic retrieval, you need to also evaluate the quality of your embeddings. As discussed in Chapter 3, embeddings can be evaluated independently. They are considered good if more similar documents have closer embeddings. Embeddings can also be evaluated by how well they work for specific tasks. The MTEB benchmark, Muenighoff et al., 2023, evaluates embeddings for a broad range of tasks including retrievals, classification, and clustering. The quality of a retriever should also be evaluated in the context of the whole RAG system. Ultimately, a retriever is good if it helps the system generate high-quality answers. Evaluating outputs of generative models is discussed in Chapters 3 and 4. Whether the performance promise of a semantic retrieval system is worth pursuing depends on how much you prioritize cost and latency, particularly during the query ing phase. Since much of RAG latency comes from output generation, especially for long outputs, the added latency by query embedding generation and vector search might be minimal compared to the total RAG latency. Even so, the added latency still can impact user experience. Another concern is cost. Generating embeddings costs money. This is especially an issue if your data changes frequently and requires frequent embedding regeneration. Imagine having to generate embeddings for 100 million documents every day. Depending on what vector databases you use, vector storage and vector search (KRIES) can be expensive, too. It's not uncommon to see a company's vector database spending be 1/5 or even half of their spending on model APIs. Table 6.2 shows a side-by-side comparison of term-based retrieval and embedding-based retrieval. Table 6.2. Term-based retrieval and semantic retrieval by speed, performance, and cost. Term-based retrieval embedding-based retrieval querying speed much faster than embedding-based retrieval query embedding generation and vector search can be slow performance typically strong performance out of the box, but hard to improve can retrieve wrong documents due to term ambiguity can outperform term-based retrieval with fine-tuning allows for the use of more natural queries, as it focuses on semantics instead of terms cost much cheaper than embedding-based retrieval embedding, vector. Storage and vector search solutions can be expensive RAG 265. With retrieval systems, you can make certain trade-offs between indexing and query ing. The more detailed the index is, the more accurate the retrieval process will be, but the indexing process will be slower and more memory-consuming. Imagine building an index of potential customers. Adding more details e.g., name, company, email, phone, interests, makes it easier to find relevant people but takes longer to build and requires more storage. In general, a detailed index like HNSW provides high accuracy and fast query times but requires significant time and memory to build. In contrast, a simpler index like LSH is quicker and less memory-intensive to create, but it results in slower and less accurate queries. The ANN Benchmarks website compares different ANN algorithms on multiple datasets using 4 main metrics, taking into account the trade-offs between indexing and querying. These include the following: recall the fraction of the nearest neighbors found by the algorithm. Query per second, QPS, the number of queries the algorithm can handle per second. This is crucial for high-traffic applications. Build time, the time required to build the index. This metric is especially important if you need to frequently update your index, e.g., because your data changes. Index size, the size of the index created by the algorithm, which is crucial for assessing its scalability and storage requirements. Additionally, BEIR, Benchmarking IR, Thakur et al., 2021, is an evaluation harness for retrieval. It supports retrieval systems across 14 common retrieval benchmarks. To summarize, the quality of a RAG system should be evaluated both component by component and end-to-end. To do this, you should do the following things: 1. Evaluate the retrieval quality. 2. Evaluate the final RAG outputs. 3. Evaluate the embeddings, for embedding-based retrieval. Combining retrieval algorithms. Given the distinct advantages of different retrieval algorithms, a production retrieval system typically combines several approaches. Combining term-based retrieval and embedding-based retrieval is called hybrid search. 266, Chapter 6, RAG and Agents. Different algorithms can be used in sequence. First, a cheap, less precise retriever, such as a term-based system, fetches candidates. Then, a more precise but more expensive mechanism, such as k-nearest neighbors, finds the best of these candidates. This second step is also called re-ranking. For example, given the term transformer, you can fetch all documents that contain the word transformer, regardless of whether they are about the electric device, the neural architecture, or the movie. Then you use vector search to find among these documents those that are actually related to your transformer query. As another example, consider the query who's responsible for the most sales to X. First, you might fetch all documents associated with X using the keyword X. Then, you use vector search to retrieve the context associated with who's responsible for the most sales. Different algorithms can also be used in parallel as an ensemble. Remember that a retriever works by ranking documents by their relevance scores to the query. You can use multiple retrievers to fetch candidates at the same time, then combine these different rankings together to generate a final ranking. An algorithm for combining different rankings is called reciprocal rank fusion, RRF, Cormack et al., 2009. It assigns each document a score based on its ranking by a retriever. Intuitively, if it ranks first, its score is 1 to 1 equals 1. If it ranks second, its score is 1/2 equals 0. 5. The higher it ranks, the higher its score. A document's final score is the sum of its scores with respect to all retrievers. If a document is ranked first by one retriever and second by another retriever, its score is 1 plus 0. 5 is equal to 1. 5. This example is an oversimplification of RRF, but it shows the basics. The actual formula for a document D is more complicated, as follows: score, D, equals sigma I equals 1n1k plus Ri, D. N is the number of ranked lists. Each ranked list is produced by a retriever. Ri, D, is the rank of the document by the retriever I. K is a constant to avoid division by 0 and to control the influence of lower-ranked documents. A typical value for K is 60. Retrieval optimization. Depending on the task, certain tactics can increase the chance of relevant documents being fetched. For tactics discussed here are chunking strategy, re-ranking, query rewriting, and contextual retrieval. Chunking strategy. How your data should be indexed depends on how you intend to retrieve it later. The last section covered different retrieval algorithms and their respective indexing strategies. There, the discussion was based on the assumption that documents have already been split into manageable chunks. In this section, I'll cover different chunking strategies. This is an important consideration because the chunking strategy you use can significantly impact the performance of your retrieval system. The simplest strategy is to chunk documents into chunks of equal length based on a certain unit. Common units are characters, words, sentences, and paragraphs. For example, you can split each document into chunks of 2048 characters or 512 words. You can also split each document so that each chunk can contain a fixed number of sentences, such as 20 sentences, or paragraphs, such as each paragraph is its own chunk. You can also split documents recursively using increasingly smaller units until each chunk fits within your maximum chunk size. For example, you can start by splitting a document into sections. If a section is too long, split it into paragraphs. If a paragraph is still too long, split it into sentences. This reduces the chance of related texts being arbitrarily broken off. Specific documents might also support creative chunking strategies. For example, there are splitters developed especially for different programming languages. Q&A documents can be split by question or answer pair, where each pair makes up a chunk. Chinese texts might need to be split differently from English texts. When a document is split into chunks without overlap, the chunks might be cut off in the middle of important context, leading to the loss of critical information. Consider the text "I left my wife a note." If it's split into "I left my wife" and a note, neither of these two chunks conveys the key information of the original text. Overlapping ensures that important boundary information is included in at least one chunk. If you set the chunk size to be 2048 characters, you can perhaps set the overlapping size to be 20 characters. The chunk size shouldn't exceed the maximum context length of the generative model. For the embedding-based approach, the chunk size also shouldn't exceed the embedding model's context limit. You can also chunk documents using tokens, determined by the generative model's tokenizer, as a unit. Let's say that you want to use Llama 3 as your generative model. You then first tokenize documents using Llama 3's tokenizer. You can then split documents into chunks using tokens as the boundaries. Chunking by tokens makes it easier to work with downstream models. However, the downside of this approach is that if you switch to another generative model with a different tokenizer, you'd need to re-index your data. 268, Chapter 6, RAG and Agents. Regardless of which strategy you choose, chunk sizes matter. A smaller chunk size allows for more diverse information. Smaller chunks mean that you can fit more chunks into the model's context. If you have the chunk size, you can fit twice as many chunks. More chunks can provide a model with a wider range of information, which can enable the model to produce a better answer. Small chunk sizes, however, can cause the loss of important information. Imagine a document that contains important information about the topic X throughout the document, but X is only mentioned in the first half. If you split this document into two chunks, the second half of the document might not be retrieved, and the model won't be able to use its information. Smaller chunk sizes can also increase computational overhead. This is especially an issue for embedding-based retrieval. Having the chunk size means that you have twice as many chunks to index and twice as many embedding vectors to generate and store. Your vector search space will be twice as big, which can reduce the query speed. There is no universal best chunk size or overlap size. You have to experiment to find what works best for you. Re-ranking: the initial document rankings generated by the retriever can be further re-ranked to be more accurate. Re-ranking is especially useful when you need to reduce the number of retrieved documents, either to fit them into your model's context or to reduce the number of input tokens. One common pattern for re-ranking is discussed in Combining Retrieval Algorithms on page 266. A cheap but less precise retriever fetches candidates, then a more precise but more expensive mechanism re-ranks these candidates. Documents can also be re-ranked based on time, giving higher weight to more recent data. This is useful for time-sensitive applications such as news aggregation, chat with your emails, e.g., a chatbot that can answer questions about your emails, or stock market analysis. Context re-ranking differs from traditional search re-ranking in that the exact position of items is less critical. In search, the rank, e.g., first or fifth, is crucial. In context re-ranking, the order of documents still matters because it affects how well a model can process them. Models might better understand documents at the beginning and end of the context, as discussed in Context Length and Context Efficiency on page 218. However, as long as a document is included, the impact of its order is less significant compared to search ranking. Query rewriting is also known as query reformulation, query normalization, and sometimes query expansion. Consider the following conversation. User: when was the last time John Doe bought something from us? AI: John last bought a fruity fedora hat from us 2 weeks ago, on January 3, 2030. User: how about Emily Doe? The last question, how about Emily Doe, is ambiguous without context. If you use this query verbatim to retrieve documents, you'll likely get irrelevant results. You need to rewrite this query to reflect what the user is actually asking. The new query should make sense on its own. In this case, the query should be rewritten to when was the last time Emily Doe bought something from us? While I put query rewriting in RAG on page 253, query rewriting isn't unique to RAG. In traditional search engines, query rewriting is often done using heuristics. In AI applications, query rewriting can also be done using other AI models, using a prompt similar to given the following conversation. Rewrite the last user input to reflect what the user is actually asking. Figure 6.4 shows how ChatGPT rewrote the query using this prompt. Figure 6.4. You can use other generative models to rewrite queries. Query rewriting can get complicated, especially if you need to do identity resolution or incorporate other knowledge. For example, if the user asks, how about his wife, you will first need to query your database to find out who his wife is. If you don't have this information, the rewriting model should acknowledge that this query isn't solvable instead of hallucinating a name, leading to a wrong answer. 270 Chapter 6, RAG and Agents. Some teams have told me that their retrieval systems work best when the data is organized in a question and answer format. Contextual retrieval. The idea behind contextual retrieval is to augment each chunk with relevant context to make it easier to retrieve the relevant chunks. A simple technique is to augment a chunk with metadata like tags and keywords. For e-commerce, a product can be augmented by its description and reviews. Images and videos can be queried by their titles or captions. The metadata may also include entities automatically extracted from the chunk. If your document contains specific terms like the error code EADDRNOTAVAIL 99, adding them to the document's metadata allows the system to retrieve it by that keyword, even after the document has been converted into embeddings. You can also augment each chunk with the questions it can answer. For customer support, you can augment each article with related questions. For example, the article on how to reset your password can be augmented with queries like how to reset password. I forgot my password, I can't log in, or even help, I can't find my account. If a document is split into multiple chunks, some chunks might lack the necessary context to help the retriever understand what the chunk is about. To avoid this, you can augment each chunk with the context from the original document, such as the original document's title and summary. Anthropic used AI models to generate a short context, usually 50 to 100 tokens, that explains the chunk and its relationship to the original document. Here's the prompt Anthropic used for this purpose. Anthropic, 2024 document, _document, /document. Here is the chunk we want to situate within the whole document, chunk _content, /chunk. Please give a short, succinct context to situate this chunk within the overall document for the purposes of improving search retrieval of the chunk. Answer only with the succinct context and nothing else. The generated context for each chunk is prepended to each chunk, and the augmented chunk is then indexed by the retrieval algorithm. Figure 6.5 visualizes the process that Anthropic follows. Figure 6.5. Anthropic augments each chunk with a short context that situates this chunk within the original document, making it easier for the retriever to find the relevant chunks given a query. Image from Introducing Contextual Retrieval, Anthropic, 2024. Evaluating retrieval solutions. Here are some key factors to keep in mind when evaluating a retrieval solution. What retrieval mechanisms does it support? Does it support hybrid search? If it's a vector database, what embedding models and vector search algorithms does it support? How scalable is it, both in terms of data storage and query traffic? Does it work for your traffic patterns? How long does it take to index your data? How much data can you process, such as add/delete, in bulk at once? What's its query latency for different retrieval algorithms? If it's a managed solution, what's its pricing structure? Is it based on the document/vector volume or on the query volume? This list doesn't include the functionalities typically associated with enterprise solutions such as access control, compliance, data plane and control plane separation, etc. 272, Chapter 6, RAG and Agents. RAG beyond texts. The last section discussed text-based RAG systems where the external data sources are text documents. However, external data sources can also be multimodal and tabular data. Multimodal RAG. If your generator is multimodal, its contexts might be augmented not only with text documents but also with images, videos, audio, etc., from external sources. I'll use images in the examples to keep the writing concise, but you can replace images with any other modality. Given a query, the retriever fetches both text and images relevant to it. For example, given what's the color of the house in the Pixar movie Up, the retriever can fetch a picture of the house in Up to help the model answer, as shown in Figure 6.6. Figure 6.6. Multimodal RAG can augment a query with both text and images. The real image from Up is not used, for copyright reasons. If the images have metadata, such as titles, tags, and captions, they can be retrieved using the metadata. For example, an image is retrieved if its caption is considered relevant to the query. If you want to retrieve images based on their content, you'll need to have a way to compare images to queries. If queries are texts, you'll need a multimodal embedding model that can generate embeddings for both images and texts. Let's say you use Clip, Radford et al., 2021, as the multimodal embedding model. The retriever works as follows: RAG 273. Generate clip embeddings for all your data, both texts and images, and store them in a vector database. 2. Given a query, generate its clip embedding. 3. Query in the vector database for all images and texts whose embeddings are close to the query embedding. RAG with tabular data. Most applications work not only with unstructured data like texts and images but also with tabular data. Many queries might need information from data tables to answer. The workflow for augmenting a context using tabular data is significantly different from the classic RAG workflow. Imagine you work for an e-commerce site called Kitty Vogue that specializes in cat fashion. This store has an order table named Sales, as shown in Table 6.3. Table 6.3. An example of an order table, Sales, for the imaginary e-commerce site Kitty Vogue. Order ID timestamp product ID product unit price, $, units total 1. 2044 Meow Mix seasoning 10. 99 110. 99 2. 3492 per and shake 25253. 2045 Fruity Fedora 18118. To generate a response to the question, how many units of Fruity Fedora were sold in the last 7 days, your system needs to query this table for all orders involving Fruity Fedora and sum the number of units across all orders. Assume that this table can be queried using SQL. The SQL query might look like this: select sum, units, as total units sold from sales where product name equals Fruity Fedora and timestamp equals date sub, date, interval 7 day. The workflow is as follows, visualized in figure 6.7. To run this workflow, your system must have the ability to generate and execute the SQL query. 1. Text to SQL. Based on the user query and the provided table schemas, determine what SQL query is needed. Text to SQL is an example of semantic parsing, as discussed in Chapter 2. 2. SQL execution. Execute the SQL query. 3. Generation. Generate a response based on the SQL result and the original user query. 274, Chapter 6, RAG and Agents. Figure 6.7. A RAG system that augments context with tabular data. For the text-to-SQL step, if there are many available tables whose schemas can't all fit into the model context, you might need an intermediate step to predict what tables to use for each query. Text-to-SQL can be done by the same generator that generates the final response or a specialized text-to-SQL model. In this section, we've discussed how tools such as retrievers and SQL executors can enable models to handle more queries and generate higher quality responses. Would giving a model access to more tools improve its capabilities even more? Tool use is a core characteristic of the agentic pattern, which we'll discuss in the next section. Intelligent agents are considered by many to be the ultimate goal of AI. The classic book by Stuart Russell and Peter Norvig, Artificial Intelligence, A Modern Approach, Prentice Hall, 1995, defines the field of artificial intelligence research as the study and design of rational agents. The unprecedented capabilities of foundation models have opened the door to agentic applications that were previously unimaginable. These new capabilities make it finally possible to develop autonomous, intelligent agents to act as our assistants, co-workers, and coaches. They can help us create a website, gather data, plan a trip, do market research, manage a customer account, automate data entry, prepare us for interviews, interview our candidates, negotiate a deal, etc. The possibilities seem endless, and the potential economic value of these agents is enormous. Agents 275. 10 Artificial Intelligence, A Modern Approach, 1995, defines an agent as anything that can be viewed as perceive its environment through sensors and acting upon that environment through actuators. AI-powered agents are an emerging field, with no established theoretical frameworks for defining, developing, and evaluating them. This section is a best effort attempt to build a framework from the existing literature, but it will evolve as the field does. Compared to the rest of the book, this section is more experimental. This section will start with an overview of agents, and then continue with two aspects that determine the capabilities of an agent: tools and planning. Agents, with their new modes of operations, have new modes of failures. This section will end with a discussion on how to evaluate agents to catch these failures. Even though agents are novel, they are built upon concepts that have already appeared in this book, including self-critique, chain of thought, and structured outputs. Agent overview. The term agent has been used in many different engineering contexts, including but not limited to a software agent, intelligent agent, user agent, conversational agent, and reinforcement learning agent. So, what exactly is an agent? An agent is anything that can perceive its environment and act upon that environment. 10. This means that an agent is characterized by the environment it operates in and the set of actions it can perform. The environment an agent can operate in is defined by its use case. If an agent is developed to play a game, e.g., Minecraft, Go, Dota, that game is its environment. If you want an agent to scrape documents from the internet, the environment is the internet. If your agent is a cooking robot, the kitchen is its environment. A self-driving car agent's environment is the road system and its adjacent areas. The set of actions an AI agent can perform is augmented by the tools it has access to. Many generative AI-powered applications you interact with daily are agents with access to tools, albeit simple ones. ChatGPT is an agent. It can search the web, execute Python code, and generate images. RAG systems are agents, and text retrievers, image retrievers, and SQL executors are their tools. There's a strong dependency between an agent's environment and its set of tools. The environment determines what tools an agent can potentially use. For example, if the environment is a chess game, the only possible actions for an agent are the valid chess moves. However, an agent's tool inventory restricts the environment it can operate. 276, Chapter 6, RAG and Agents. For example, if a robot's only action is swimming, it'll be confined to a water environment. Figure 6.8 shows a visualization of SWE agent, Yang et al., 2024, an agent built on top of GPT-4. Its environment is the computer with the terminal and the file system. Its set of actions include navigate repo, search files, view files, and edit lines. Figure 6.8. SWE agent, Yang et al., 2024, is a coding agent whose environment is the computer and whose actions include navigation, search, and editing. Adapted from an original image licensed under CC by 4.0. An AI agent is meant to accomplish tasks typically provided by the users in the inputs. In an AI agent, AI is the brain that processes the information it receives, including the task and feedback from the environment, plans a sequence of actions to achieve this task, and determines whether the task has been accomplished. Let's get back to the RAG system with tabular data in the Kitty Vogue example. This is a simple agent with 3 actions: response generation, SQL query generation, and SQL query execution. Given the query, project the sales revenue for Fruity Fedora over the next 3 months, the agent might perform the following sequence of actions. 1. Reason about how to accomplish this task. It might decide that to predict future sales, it first needs the sales numbers from the last 5 years. Note that the agent's reasoning is shown as its intermediate response. 2. Invoke SQL query generation to generate the query to get sales numbers from the last 5 years. 3. Invoke SQL query execution to execute this query. 4. Reason about the tool outputs and how they help with sales prediction. It might decide that these numbers are insufficient to make a reliable projection, perhaps because of missing values. It then decides that it also needs information about past marketing campaigns. Agents 277. 11. A complaint in the early days of agents is that agents are only good for burning through your API credits. Invoke SQL query generation to generate the queries for past marketing campaigns. 6. Invoke SQL query execution. 7. Reason that this new information is sufficient to help predict future sales. It then generates a projection. 8. Reason that the task has been successfully completed. Compared to non-agent use cases, agents typically require more powerful models for 2 reasons: compound mistakes. An agent often needs to perform multiple steps to accomplish a task, and the overall accuracy decreases as the number of steps increases. If the model's accuracy is 95% per step, over 10 steps, the accuracy will drop to 60%, and over 100 steps, the accuracy will be only 0.6%. Higher stakes. With access to tools, agents are capable of performing more impactful tasks, but any failure could have more severe consequences. A task that requires many steps can take time and money to run. 11. However, if agents can be autonomous, they can save a lot of human time, making their costs worthwhile. Given an environment, the success of an agent in an environment depends on the tool inventory it has access to and the strength of its AI planner. Let's start by looking into different kinds of tools a model can use. Tools. A system doesn't need access to external tools to be an agent. However, without external tools, the agent's capabilities would be limited. By itself, a model can typically perform one action, for example, an LLM can generate text, and an image generator can generate images. External tools make an agent vastly more capable. Tools help an agent to both perceive the environment and act upon it. Actions that allow an agent to perceive the environment are read-only actions, whereas actions that allow an agent to act upon the environment are write actions. This section gives an overview of external tools. How tools can be used will be discussed in planning on page 281. The set of tools an agent has access to is its tool inventory. Since an agent's tool inventory determines what an agent can do, it's important to think through what in 278, Chapter 6, RAG and Agents. How many tools to give an agent? More tools give an agent more capabilities. However, the more tools there are, the more challenging it is to understand and utilize them well. Experimentation is necessary to find the right set of tools, as discussed in Tool Selection on page 295. Depending on the agent's environment, there are many possible tools. Here are 3 categories of tools that you might want to consider: knowledge augmentation, i.e., context construction, capability extension, and tools that let your agent act upon its environment. Knowledge augmentation. I hope that this book, so far, has convinced you of the importance of having the relevant context for a model's response quality. An important category of tools includes those that help augment your agent's knowledge of your agent. Some of them have already been discussed: text retriever, image retriever, and SQL executor. Other potential tools include internal people search, an inventory API that returns the status of different products, Slack retrieval, an email reader, etc. Many such tools augment a model with your organization's private processes and information. However, tools can also give models access to public information, especially from the internet. Web browsing was among the earliest and most anticipated capabilities to be incorporated into chatbots like ChatGPT. Web browsing prevents a model from going stale. A model goes stale when the data it was trained on becomes outdated. If the model's training data was cut off last week, it won't be able to answer questions that require information from this week unless this information is provided in the context. Without web browsing, a model won't be able to tell you about the weather, news, upcoming events, stock prices, flight status, etc. I use web browsing as an umbrella term to cover all tools that access the internet, including web browsers and specific APIs such as search APIs, news APIs, GitHub APIs, or social media APIs such as those of X, LinkedIn, and Reddit. While web browsing allows your agent to reference up-to-date information to generate better responses and reduce hallucinations, it can also open up your agent to the cesspools of the internet. Select your internet APIs with care. Capability extension. The second category of tools to consider are those that address the inherent limitations of AI models. They are easy ways to give your model a performance boost. For example, AI models are notorious for being bad at math. If you ask a model what is 199,999 divided by 292, the model will likely fail. However, this calculation is trivial if agent's 279. The model has access to a calculator. Instead of trying to train the model to be good at arithmetic, it's a lot more resource efficient to just give the model access to a tool. Other simple tools that can significantly boost a model's capability include a calendar, time zone converter, unit converter, e.g., from LBS to KG, and translator that can translate to and from the languages that the model isn't good at. More complex but powerful tools are code interpreters. Instead of training a model to understand code, you can give it access to a code interpreter so that it can execute a piece of code, return the results, or analyze the code's failures. This capability lets your agents act as coding assistants, data analysts, and even research assistants that can write code to run experiments and report results. However, automated code execution comes with the risk of code injection attacks, as discussed in Defensive Prompt Engineering on page 235. Proper security measurements are crucial to keep you and your users safe. External tools can make a text-only or image-only model multimodal. For example, a model that can generate only texts can leverage a text-to-image model as a tool, allowing it to generate both texts and images. Given a text request, the agent's AI planner decides whether to invoke text generation, image generation, or both. This is how ChatGPT can generate both text and images. It uses DALL-E as its image generator. Agents can also use a code interpreter to generate charts and graphs, a LaTeX compiler to render math equations, or a browser to render web pages from HTML code. Similarly, a model that can process only text inputs can use an image captioning tool to process images and a transcription tool to process audio. It can use an OCR, optical character recognition, tool to read PDFs. Tool use can significantly boost a model's performance compared to just prompting or even fine-tuning. Chameleon, Liu et al., 2023, shows that a GPT-4-powered agent, augmented with a set of 13 tools, can outperform GPT-4 alone on several benchmarks. Examples of tools this agent used are knowledge retrieval, a query generator, an image captioner, a text detector, and Bing search. On Science QA, a science question answering benchmark, Chameleon improves the best published few-shot result by 11.37%. On TabMWP, Tabular Math Word Problems, Liu et al., 2022, a benchmark involving tabular math questions, Chameleon improves the accuracy by 17%. Write actions. So far, we've discussed read-only actions that allow a model to read from its data sources. But tools can also perform write actions, making changes to the data sources. A SQL executor can retrieve a data table, read, but can also change or delete the table. 280 Chapter 6, RAG and Agents. Write. An email API can read an email but can also respond to it. A banking API can retrieve your current balance but can also initiate a bank transfer. Write actions enable a system to do more. They can enable you to automate the whole customer outreach workflow, researching potential customers, finding their contacts, drafting emails, sending first emails, reading responses, following up, extracting orders, updating your databases with new orders, etc. However, the prospect of giving AI the ability to automatically alter our lives is frightening. Just as you shouldn't give an intern the authority to delete your product tie-in database, you shouldn't allow an unreliable AI to initiate bank transfers. Trust in the system's capabilities and its security measures is crucial. You need to ensure that the system is protected from bad actors who might try to manipulate it into perform harmful actions. When I talk about autonomous AI agents to a group of people, there is often someone who brings up self-driving cars. What if someone hacks into the car to kidnap you? While the self-driving car example seems visceral because of its physicality, an AI system can cause harm without a presence in the physical world. It can manipulate the stock market, steal copyrights, violate privacy, reinforce biases, spread misinformation and propaganda, and more, as discussed in Defensive Prompt Engineering on page 235. These are all valid concerns, and any organization that wants to leverage AI needs to take safety and security seriously. However, this doesn't mean that AI systems should never be given the ability to act in the real world. If we can get people to trust a machine to take us into space, I hope that one day, security measures will be sufficient for us to trust autonomous AI systems. Besides, humans can fail, too. Person ally, I would trust a self-driving car more than the average stranger to drive me around. Just as the right tools can help humans be vastly more productive, can you imagine doing business without Excel or building a skyscraper without cranes? Tools enable models to accomplish many more tasks. Many model providers already support tool use with their models, a feature often called function calling. Going forward, I would expect function calling with a wide set of tools to be common with most models. Planning at the heart of a foundation model agent is the model responsible for solving a task. A task is defined by its goal and constraints. For example, one task is to schedule a 2-week trip from San Francisco to India with a budget of $5,000. The goal is the 2-week trip. The constraint is the budget. Agents 281. Complex tasks require planning. The output of the planning process is a plan, which is a roadmap outlining the steps needed to accomplish a task. Effective planning. Type E. Cali requires the model to understand the task, consider different options to achieve this task, and choose